Okay, so I believe we can start with the second session of today. We will have two talks, and the second talk by Anna Sanpera was replaced by the talk by the IUPAP winner. So before I start, let me just express my appreciation. Also, my name is Dieter Meschede, and my first ICAP was in 1980, and I met several of you. I think several of you will share this. Maybe Jerry, I'm not sure, and some others for 36 years. And I'm really pleased to see that it's as vivid as it ever was, and it's a very good conference. So thank you to our Korean colleagues. So now let's immediately start. This is a session on quantum statistical physics and matter wave interferometry, and I'm glad to announce Philippe BOUYER from Bordeaux on advances in airborne and underground interferometry.
Thank you very much. I would like to first thank the organizer for the opportunity to come here to this very nice conference, ICAP. I just realized that it's also quite special because Professor J pioneered 20 years ago a trap using Axicon on pyramids that actually is at the base of a big development we had on compact atom interferometer. So it's a real pleasure to be here. I will take this opportunity to give you an overview of the development we are doing in Bordeaux on atom interferometry, but outside of the lab, either in a plane or also the project we have to build a big instrument underground. So I don't have any batteries anymore. Or maybe it's back. I will mainly focus on light pulse-based cold atom interferometry, where I will use some set of cold atoms at temperature of about a microkelvin or so, and send it through 3 light pulses made with standing waves that will diffract the atomic matter waves so that we can split, deflect, and recombine the 2 trajectories in order to build an interferometer. We will detect the fringes simply by fluorescence detection. I also will only focus here on measuring acceleration very precisely with matter wave interferometry, and I just want to give you a very simple picture to understand how the sensitivity of those interferometers come into play and why it is potentially so sensitive. The very simple picture is that at each time you actually shine this optical standing wave to manipulate the wave packets, you imprint on the wave packet some information about the position of its center of mass. And simply, you can understand in this case that the matter wave interferometer is monitoring very precisely the distance the atoms traveled during the time you're doing the interferometer. This distance, if you are in free fall, being simply proportional to the acceleration, g if it's gravity, times the square of the time between the pulses, t squared. And basically, the dephasing or the phase shift you measure in the interferometer is simply the distance divided by the reference distance you have for the measurement, which is the optical wavelength. So this simple equation, which is actually accurate at first order, tells you that the scale factor of this interferometer is extremely well known. You can define wavelengths and time very precisely, so that in principle, you can very accurately measure acceleration with those systems. In addition to that, if you put some numbers, you realize that you can be extremely sensitive. If I take the example of a signal-to-noise ratio of 1,000, which means that I can detect milliradians of phase difference in the interferometer, and a time between the pulses of 1 second, I can measure variation of acceleration of the order of 10 to the minus 10 meters per second squared. And if you are a geophysicist, that tells you that you have a resolution of 10 nanogal, a gal being 10 to the minus 9 G. And if you integrate for some time, for example, for 3 hours, you're taking measurements every second for 3 hours, and then you can reach the level of a picogal or even less, and that's the best measurements you can do so far on accelerometry. So the prospect of using this accelerometer to very high precision actually led us to take all these instruments out of the laboratory, and actually now we try to scatter them everywhere from the surface of the Earth by, for example, building or using transportable interferometers to space. There are some space projects. There are even some space programs to put on the International Space Station. And I will focus here on two other aspects that are somewhat important for the future, I think. It's to develop interferometry in mobile systems like a plane. I will discuss about the development we have on a dual species atom interferometer, and also the prospect of really reaching ultimate sensitivities if you go underground. So I will start focusing on the experiments we have been developing now for quite some years on the dual species atom interferometers in a plane. The aim of these experiments initially is to test the universality of freefall by comparing the acceleration of two different atomic species. But also because you're in this moving vehicle, you can really test all the problems or all the solutions you have to find in order to really use those systems for mobile operation or for navigation. So the first thing is you need to build an experiment, and the experiments we have in Bordeaux is not a compact sensors that can be applied for commercial purposes. It's really a moving laboratory. First, we have to move it from our institute to the plane each time we have to fly. And we can really upgrade and change these experiments at will, changing the configuration. What we have nowadays is a fairly compact sensor head, which is here. So the head itself is about 20 centimeters, and we can do 3-axis acceleration measurements, dual species interferometry, etc. So as I told you before, we focused on dual species interferometry to compare actually the acceleration between two species. So the first species is rubidium. I will not tell a lot about it because there are lots of rubidium interferometers working, and they actually work really well. Rubidium is a very nice atom. Then we picked up potassium because the mass is half the mass of rubidium, because the wavelength is very close. But potassium is not a very nice atom to do interferometry because basically the hyperfine splitting is very small, so it's hard to cool and it's hard to make the right state selection in order to get high contrast in the interferometer. So we had to work a little bit more in order to get to low temperature, simply, for example, by developing some well-known technique that has been used a long time ago of blue molasses or gray molasses in order to go down to a much lower temperature, and also some protocols for purification of the states in order to really have the states, the non-magnetic states we want to use for interferometry. This allowed us to reach a signal-to-noise ratio of about 100 with this interferometer, and we actually now have a potassium interferometer which works better than our rubidium interferometer, mostly for technical reasons, and which is almost reaching 10 nanogals of resolution after integration, which is a little bit more than the state of the art, but which is very good for this kind of experiment. So now we have the two interferometers operating together. We still have some systematic effects that do not allow me today to give a number on the equivalence principle. But with the potassium, for example, we start to compare very favorably with the tide model, and this is the compensation of the tide model that is showing that actually instead of this bump that is mostly due to some laser technical problems, we really have a nice integration on this system. The major aspects of the experiment is to make it work in the plane. And while you all flew, or lots of you flew to come here, a plane is really far from the best environment to make high precision measurements. And the first reason why it's that is it's actually vibrating like hell, and the plane we use, which is a specific plane which is flying in a parabolic flight to give us some microgravity time, is actually even worse. I mean, it's really shaking like hell. The amplitude of acceleration noise is roughly 1 meter or 2 meters per second squared. So if you want to measure micrometers or nanometers per second squared, you really have a long path to go in order to measure that. So basically, if you run your interferometer in the plane, you see nothing. You just see a random distribution of points. But if you look at the statistic of this distribution, you find that the statistics follows exactly what you would have if you would actually see a signal which is a sinusoidal signal of a certain contrast or amplitude with a certain mean value and a certain noise. And so from these statistics, you have all the information you miss about the interferometer, the rest being the scale factor that you know very well. So now if you correlate the two measurements, you're able either to reconstruct the fringes or by integrating the noise in the frequency band response of your interferometer, to know on which fringe you are, and then use the atom interferometer to get a high precision about the residual acceleration that you cannot resolve with your classical accelerometer. This way you can reconstruct the acceleration, and with these experiments we were able to improve the acceleration measurement from what was done with classical accelerometer by more than 2 orders of magnitude. Acceleration is a big thing, but apparently we can solve it quite easily by just correlating with classical accelerometers. Rotation is another problem. And what's nice with this parabolic flight is actually we have 2 phases, one where the rotation is quite small, and one when the rotation is really big. During the parabolic flight, it's 5 degrees per second rotation. And during this rotation, actually, you have a Coriolis acceleration, which will have a strong effect on your interferometer. The first one is it gives you an additional phase shift, but this is normal. I mean, even when you measure gravity on ground, you actually measure not only gravity, but you're measuring the acceleration of gravity plus the centrifugal force due to the rotation of the Earth. So this is taken care of in the measurement. But the other thing is if the Coriolis effect is too large, it will affect the trajectories of the atom, and at the end, the interferometer does not close anymore. And if your coherent length is smaller than the spacing between the two trajectories, then you will lose contrast. And actually, that's what we see on the experiment. If you are in the 1G phase, you can increase the time to a certain extent, a few milliseconds. I will come back on that later. But now, if you are in this highly rotation phase, the contrast drops, and it drops even faster if you are with hotter atoms because the coherent length is smaller. So this is a model that takes all this into account, and it shows that if you want to operate outside of the lab, you have to cope with this rotation. And actually, from this measurement, if you say now I want to put an accelerometer in space on a low Earth orbit, where the rotation rate is roughly a few degrees per second, you realize that if you want to do 5 seconds of interrogation time, then you need to compensate the rotation by 5 to 6 orders of magnitude. You need to have a residual rotation which is 50 times lower than the rotation of the Earth. And so this is a very demanding aspect. You have to correct to this. So this is done, for example, on ground to beat this 50 times when you do a few seconds of interrogation by rotating the retroreflecting mirror, which is creating the standing wave. For navigation, if you translate this problem to navigation, it's a really big problem because the plane will fly somewhat straight, but it can turn. So, which means that you have to cope with large rotation rates sometimes, and your inertial base has to work with that. And also you have to cope with large acceleration. And for example, if you have 2 meters per second squared, for a few seconds, the atom travels over a few meters, so your vacuum chamber is too small, and the atom will just crash on the walls of your vacuum chamber. So either you have to limit the time to small times, like that, or you have to find some new methods to really take advantages of the fact that the scale factor can increase if you increase the interrogation time. So there are a few ways to do it. We tried one. If you start with a simple interferometer, 3 pulses like that, what you can usually do is here you measure the population, and then you have to start again and do a new interferometer. But what you could do instead is simply do a weak measurement or a non-destructive measurement in which you measure the phase difference between the 2 outputs without destroying the quantum superposition, and then you re-inject this quantum superposition in the interferometer again. And in this case, you can repeat that many, many times, and you might integrate much faster than the square root of t time that you usually do if you just average the measurements. So we tried that, but not on an interferometer, on a clock. So the picture is somewhat the same. You create a coherent superposition, which can be described as a block vector. The block vector will rotate in the equatorial plane. That's the evolution of the phase. And if you want to measure the phase, you can rotate into the vertical plane, do a weak measurement, put it back, and let it evolve again. And you can even do better than that in order to be sure that you don't lose any information. The measurement here, you can put back into your interrogation laser or your interrogation radio frequency in order to phase lock the 2 systems. So trying that with a model clock, so it's not the best clock ever. Again, it was just a small system in a dipole trap. We were able to let's say, correct 10 times, like do substantial 10 times measurement with the clock. and have a 7 dB improvement, while if you would just average, you would have a factor 3, which is 5 dB, showing that indeed you can really take advantage of measuring weekly the phase, injecting back the quantum state, and improve faster than what you would normally do if you would just average. This 7 dB is not the best. In principle, we would expect 10 dBs, simply because you have a trade-off between the destructivity of your measurement and the amount of information you can get at each measurement, which in this case did not allow us to go beyond that. For the clock, it's quite interesting because if you're thinking now of ultimate sensitivities of clock, you might be limited in time by the phase drift or the phase noise of your reference oscillator. And in this case, you can really beat this problem by just phase locking the reference oscillator to the phase of your clock and get much longer interrogation times. Okay, so the last part of my talk, I will focus on the second experiment, which is actually an experiment we are currently building. This aims at having a large underground correlated network of accelerometers with the basic motivation is to go towards a new way of detecting or observing gravitational waves at frequency below a few hertz, which is currently the limit of the optical detectors nowadays. So this is a large program that has been funded at the end of 2011 in this investment, like government investment program. It's called an Équipement d'Excellence. And it involves 18 laboratories and institutes, laboratories being scattered over the topics of atomic physics for the atomic development, but also geophysics, because this might already give us one of the best way to study with an underground network of accelerometers how the gravity is changing around the system, and also astrophysics for the prospect of measuring and observing gravitational waves with that. The performance of this first stage, we hope to reach a gradient sensitivity of 10 to minus 13 meters per second squared per meter over 300 meters of measurements, which gives us also a strain sensitivity of about 10 to the minus 13 in terms of gravitational wave detection. And actually, the gravimeters will already be at the level of 10 to the minus 10 G, which is this 10 nanogal I was mentioning before. All this being done in about 1 second of measurement. So just to describe a little bit the experiment, so it's another scale of what we usually do in the lab. We will have a laser cavity all along this path, which is about 300 meters long. Actually, I say about because we have to drill on the ground the mountain, and the length of the tube will depend on how much they can progress with the money we give them. So it might be 250 meters, it might be 400 meters, depending on how difficult it is for them to do it. And every 50 meters, we have some places where we can actually plug in an atom interferometer. I will come back on how this atom interferometer works in a second, so that we can really monitor the gravity changes and having a spatial resolution and as well as a time resolution on that. The experiment will be built with 2 arms like that in a configuration which is very similar to what you would have in a classical optical interferometer. So we have the optical readout with the cavity, and then we locally measure the variation of acceleration with the atoms. So this is currently under discussion for the contract. The drilling of the cavities to install this should start at the end of this year. What we have now is the first stage, which is the sensor head. So that's the first one, and we will have 5 with the budget that we obtained from the French government for that. So this, again, if you start these big programs, you have to be fairly conservative. Otherwise, they do not trust you to achieve the construction of such instrument in time. So this is a very standard system with a 2D MOT, 2D rubidium MOT, sending about 10 to the 9 atoms per second in a 3D MOT. We launch these atoms vertically. We make a velocity selection in the direction of the interrogation beam to get subrachial velocities. And we have here about 1 million atoms that will cross 2 beams. the first one being making the first and the last pi over 2 pulse, and the top one being making the pi pulse for the interferometer. Here we have, in this configuration, which is a smaller one, we have about 100 milliseconds of interrogation. Ultimately, in the final system, we'll have about 500 to 600 milliseconds of interrogation time for our sensor. So as I told you, the motivation is to make a first big step towards the observation of gravitational waves with cold atom interferometers. Of course, this motivation has been amplified with the recent discovery of gravitational waves that was done with LIGO. The first observation was done in September last year, and there was a second one a few weeks or a few months ago. And so basically what they observed is the in-spiral, the last phase of the in-spiral and the merger of two compact binary systems. So this is the merger where the frequency increases and the amplitude decreases. And basically, if you look at the sensitivity curve of LIGO or Virgo or even the future generation, they kind of stop between 1 Hertz and 10 Hertz because you have to suspend the mirrors, because you have to have seismic isolation, which are quite complicated at that level. And this actually limits the observation to this frequency band where you can observe, apparently with a fairly good signal-to-noise ratio because the sensitivity is very good, the merger of the system. But you don't have the resolution to observe the in-spiral phase, which can last much longer, weeks, days, weeks. And it's quite interesting, as was mentioned in this paper, to observe this phase, first because then you have plenty of time to look what's happening, and also you can then trigger the detection from for the optical detectors. So there's been numerous proposals to use atom interferometry, and there are still a lot. Actually, at Stanford University, Mark Kazevich and Jason Hogan are fairly active in making lots of propositions, especially for space application. So in this case, you compete with current proposal using laser interferometry in space, like the LISA program. You can complete it in this recent proposal by, for example, tuning your interferometer by changing the interrogation time in order to look at different type of frequency. So all these proposals are based on sending experiments to space, which is more expensive and takes time. And we really focus on the prospect of building something on ground. This is the aim of MIGA. So MIGA, which should be operating in 2018, will not have the sensitivity to observe this in-spiral phase because we have this signal-to-noise ratio, which will be about 1,000 and so on. And what we expect is first to prove that we can build such system, operate it at this level, and then progressively increase the sensitivity in order, and if you take reasonable numbers, you expect to reach this sensitivity where you can observe what has been observed so far, and there are also prospects that in this frequency band you can have other type of sources to detect. When you tell that to the experts in the field, all the people who have struggled years and years to build these optical detectors, the first thing they tell you is, this is not going to work, because if you try to do that, very soon you will reach a level where the only thing you will see is the ambient noise of your system. They call that Newtonian noise. It's basically the fact that all the masses around your instrument will move and shake. That starts from the ground, but it's also the air fluctuation, the clouds, and etc. And it creates a background noise, which is very large. It's much smaller if you go underground, and this is basically, for example, the noise we calculated from the place where we go. By the way, this place is 500 meters in the southeast of France. We were lucky enough. It's a place that was formerly the command site for the nuclear weapons of France. Now they are dismantled, and we had this for free because it was very well equipped and useless. So you need to mitigate this noise. And this is where I think the atoms come into play, and because now what you can do is not only measure the variation of the length as you would do with an optical detector, and this variation of the length comes from the fact that the metric is modified by the gravitational wave, but also because you have these free-falling mirrors, it comes from the fact that the gravitational force on the mirror can be fluctuating. But now if you put more detectors, then you can have a spatial resolution, or you can correlate, you can measure the spatial correlation of your signal. And what you expect for a gravitational wave, it's a plane wave, because it's an event which is very far away from when you did the measurement, whereas any other fluctuation will have a spatial signatures that you can actually measure and you can take it out. We did some model for that, and we showed that indeed we can be able, by using these models and the right geometry, to actually fill the gap and beat this Newtonian noise. So this is a prospect that we want to test and check with this instrument. So this brings me to the conclusion. If you were attending the poster session yesterday, or if you heard the discussions around the clock, basically, you can find out that today, I think it's a very exciting. The next year will be very exciting for atom interferometry. There are plenty of things we can do because we can reach now very high sensitivity. And this is all the list, from more application in gravimetry and navigation to more fundamental physics, like gravitational physics or beyond the standard models. And this will go through the improvement of signal-to-noise ratio by something of a few orders of magnitude, which you can do by getting higher flux. This is a fairly straightforward way, or also squeezing. There are very nice experiments of squeezing. We heard about some. There are some that have been published recently, and there are many groups working on that. And also you need to get larger areas, either by increasing the splitting due by the splitters, or by increasing the interrogation time. And there are many experiments like drop towers, big fountains, and also an Einstein elevator where you can put your experiment in an elevator, but only the experiment, because the elevator will just like push you high in order to simulate zero gravity. With that, I will stop. I would like to thank my group and my co-workers, and also advertise for next year's ICOLS, International Conference on Laser Spectroscopy, which will happen in Arcachon, so it's a very nice place. This is a picture of the sand dunes in Arcachon, which is the biggest sand dunes of Europe, Dune du Pilat. And this is a picture of Bordeaux, which is a very nice place. And I hope I will see you, a lot of you there next year. Thank you very much.
Thank you very much. And we have a few minutes for questions, not for the beach in Arcachon, but for the ICAP here today. Okay, here in front, we have a question, please.
Boyer, in your experiment using AR in air, the free contrast of the potassium is decreased quickly than the rubidium. Do you think this is caused because potassium is lighter than the rubidium?
So the decrease of the contrast of the interferometer,
yes,
so the model I put on the graph is actually including the rotation rate, so the Coriolis effect. It's really the major problem is the Coriolis effect. Then you have also other problem if you go to larger interrogation time, but here it's really the fact that it's rotating so fast that you lose contrast very, very rapidly.
Yes, so last question. What kind of atoms do you use in the on-the-ground atom interferometer?
Again, so far, as I said, we had to be conservative because this grant was supposed to be to build something and not to do any research. So we are using rubidium atoms in there. That might not be the best way for the future, but it's easy to improve once you have the infrastructure ready. But so far, it's rubidium.
Oh, thanks.
Just to clarify, if you have this tunnel and the laser beam which interrogates your many atom interferometers, that means you're measuring transverse acceleration because the beam propagates horizontally.
Yes.
And so, I mean, usually you would think gravity is vertical, but you're looking for the transverse
So now I'm
variations.
exactly. With this configuration where we interrogate with the cavity beams, we are looking at variation along the beam path. But that's where the contribution of the gravitational wave, if it goes through, will be seen by the atoms as well in this direction.
And maybe a related question is, if you want to detect a gravitational wave with this setup, I mean, what you're really seeing now is, from the atomic physics perspective, you measure the free fall of atoms at different locations, and when a gravitational wave comes through, the free fall acceleration, or little g, so to speak, changes due to the gravitational wave.
Yeah.
I mean, is that sort of completely trivial to see? Because what is, you're changing the metric of space, you're changing the metric for your vacuum chamber, for the mirrors and for everything, but in the end, that's what you're doing. You're looking for periodic variation of the gravitational acceleration.
Yes, so if I want to use another wording, what you basically do when you're taking two clouds of atoms with and interrogate with a single laser is you're measuring how during the interrogation time the phase reference between this area and this area has changed. So how the optical path has been modified. That's a way to see it if you forget about accelerations. And this is exactly what you're looking with LIGO as well. I mean, what the metric is changing is actually the time the light will take to go from one mirror to the other mirror. So basically, it's changing the phase. So you do exactly the same. So it's completely equivalent to say that you are measuring acceleration or like differential acceleration in this case, or you are measuring basically modulation of the phase between the two lasers. And that's also the problem is you cannot make a distinction between a true acceleration and a modification of the metric, even for LIGO, for example. And that's why we need this spatial resolution as well.
Thank you very much, Philippe, at this point. And I think we have to move on to the next talk. And for that, let's give the speaker once more our appreciation. And let me introduce Tokiyoshi Atsuma, who is presiding the IUPAP C15 Commission, who has also handed out a prize to young scientists. IUPAP is the organization which takes care, for instance, of our units and conferences. And so please